我刚才跟他讨论那个 piecewise regression，我说个 piecewise regression，你在那个临界点那个地方，你不能假定两个模型的那个在那个临界点处连接是 always 它是零，它那个连接变异是零。
有可能是
你不知道它是多大，你不知道是不是个降，但是你不能assume它等于零，它有个变异，变异的大小可以用来推断这两个模型是否连接。我们应该这样做，你知道吧？而不是说 always 我就可以说，我说 assume 它那个连接变异等于零，然后你去检连接方程就得到零，不能这样做的。Yeah. Sorry, we talk about in Chinese.
I enjoyed it. Well, what he talked has nothing to do with his talk. It talks about what he discussed with Dr. Powell just right now. That got some problems interesting.
Yeah. Powell said, yeah, we should take that assumption. The connection variability is always equal to 0.
I see.
But my opinion is no, we cannot take that one because that's a random system. It's not a certainty system. It's not a mathematical function. It's a random model.
We'll take a couple of minutes on this.
Okay. Where is the one?
It's over there.
Oh. Should I say it here while you introduce it?
So welcome to the Department of Bioinformatics and Biostatistics Seminar Series Spring 2020. And today our guest speaker is Dr. Ligong Chen, and he was Associate Professor at Department of Health Science and Epidemiology at the former Tungji Medical University. And he is currently working biostatistician at the University of Service University of Health Science. So please welcome Dr. Chen for his visit to our department today and the presentation.
Thank you for everybody coming, and thank you, especially thank you for Dr. Wu and Dr. Pao for giving me the opportunity. Actually, I'm humble for standing here. Actually, use as the PowerPoint showed, my background is medical, it's not mathematical. So I'm very humble to talk about my ideas, but I think after you heard this presentation, you might know this should be a big breaking through in the statistics. So as the title showed, what I'm talking is about the self-weight of continuous random variable. I sent the abstract to Paul and Dr. Wu. So the reason I'm trying to construct this self-weight is because let's considering about the normal distribution is only a special case in unimodal distributions. I mean the single peak distributions from left skewed to right skewed. The change of the distribution curve within the range is random. So the normal distribution is just a special case. So the arithmetical mean is only at the peak of all symmetric distribution curves. Even never at the peak of all skewed distribution curves. Right? This should be a common sense in statistics. So we can sure the arithmetic mean is a biased estimate for the peak of the skewed distributions. right? Yes, it's unbiased estimate for the mean, arithmetical mean, no problem. For example, sample mean is unbiased estimate for the population mean because they are homogeneous measures, no problem. We cannot say the median, sample median is unbiased estimate of the population mean, right? Of course, it's biased because they are not the same kind of measures. So this presentation is trying to introduce a unified algorithm for the peak estimation of all unimodal distributions to make the expectation estimate be unbiased. After we obtain the peak estimation, unimodal distribution curve can be cutted to two half-normal distributions, right? Just the variance might be different at this left side and the right side. If the variance at two sides are the same, are equal to each other, that's the symmetrical one, right? So we can find a certain mathematical relationship between the original distribution with its mirror image distribution. Once we find the peak, we can rotate the distribution curve around the peak, right? So we can get mirror image distributions. Right? So there's a certain mathematical relationship between these two distributions, the original one and the mirror image one. And a combined distribution of the original one with its mirror image one will be a symmetrical one, the normal one. So we have a new approach for normalization. Then the new normalization will never change the expectation estimate, the variance estimate, and also the maximum measurable space, right? Currently, we use the mathematical function to transform for normalization. That will change the expectation, variance, and the big problem is the measurable space is changing. For example, logarithm, right? Exponential. It's different from the original ones. The original scale are evenly distributed, but the exponential ones or the logarithm ones are not evenly, right? So it's actually it's a pseudo normal, even if it's normalized. Actually, we can say many skewed distribution cannot be normalized with the mathematical function transformation, right? So it's uncertain. But with this methodology, the normalization is certain, and because the normalization doesn't change anything, so the normalization is no longer necessary. Do you agree? So the foundation of statistics will be extended from the normal distribution to all the unimodal distributions, including all skewed distribution and the normal distribution, the symmetrical ones. So the so-called non-parametric method will be limited to a very small category, or even eventually you might be quit from the statistics. Yeah. Since I use the Gosset, I don't use I use the students. As you guys, I think it's the time to return this methodology to its name. The Gosset t-test can be directly applied to all skewed distributions with the peak estimation, not the arithmetical mean estimations, because the peak is unbiased estimate, And skewed distributions can be normalized without any problem, certainly, right? So, yeah, everything will be simple. Genetic data analysis might be greatly benefited from this methodology. This is a distribution. Oh, sorry. It looks like normal, right? Can anyone find anything wrong with this, in this picture? Can you find anything wrong?
No.
Look at two tails. And two tails. Do you see anything wrong? It's not a solid curve. This is actually, this is the original one. This is the full. We have the ordinate. This is the sample scales, and this is the ordinate. The ordinate is the range is from 0 to 1. It means every point in this two-dimensional space has two values. One is the original x, one is the weight, self-weight on this ordinate. So this is a scatter plot. It was not drawn with a probability density function. So new method is to tell you how to get the measure for each point.
So this is still normal random variable. You just generate.
Actually, I said this is a simulation.
Yeah.
It's with normal distribution. Assume it's a normal. Give the mu and x bar.
Oh, what's your sigma?
Sigma later. This is just to show.
Okay.
This is the beginning.
Okay.
This is the beginning. Yeah. Later I will full. Yeah. So before we go into the topic, I would like to share a simple question with you. I once asked Professor Bradley Efron if we use, if we use randomly edible variable adjective following triple x norm, right? To replace random variable, what is the best norm for replacing the triple x? Bradley replied my email. Said, yes, the random variable does mean something randomly variable. I asked this question because I was math background. I was obscured when I first time to touch the random variable. The definition in the probability theory. It's obscure for me to understand. So I asked it. So I think the attribute is the best word here. So what statistics is working on is attributes, right? Yeah, so a random variable is a randomly variable attribute. That's it. That's the definition for me. It's easy to understand. Rather than the definitions in probability theory. Okay. I also want to share another thing with you. This is a criticism from a mathematical background statistician. His name is Peter John Huebel. Have you ever heard of him? The robust regression. He's one of the founders. He is him, John Huebel. He gave a talk in November 1997 in the Institute of Mathematical Statistics in the Academy of Chinese Sciences. He said, many mathematical background statisticians are used to take a mathematical certainty thinking mode to solve the problem with uncertainty in statistics. This might make mistakes, but he felt very helpless. I think the reason might be that he was unable to find what was going wrong. Would you like to take the certainty thinking mode to solve the uncertainty problem? Dr. Paul, that's the example. There's two definitions that I proposed. One is constant expectation. I try to introduce the constant to random system, just like the zero we introduced to mathematics to digits, right? In random system, it means nothing changed. It's a norm of system. So actually we need this. We need a definition in this pattern because every random variable has this pattern, right? So the definition of constant expectation can be wrote in that way. And on the other hand, if we don't include it in the random system, we might lose an important base to discuss the random phenomena, since a statistic is a random variable to the population, but it is a certain constant to the sample itself. For example, the sample mean never change, right? So once we have the constant definitions, we know from where we can go and how to do. That's where we can arrive. The constant is not only the base and the starting point from where we may discuss the random phenomena further, but also the ending point that we try to arrive. That's why I try to introduce the constant, the definition for the constant expectation to statistics. So here, that's the, for the expectation on a sufficient statistic S defined over random space S, we have this. So a sufficient statistic is the best one to a sample over which it's defined. It means a statistic for a sample must be defined over all the sample space, the sample, not just part of sample. Yeah, in current statistics, many people do cross validations with partial sample, or use the learning sample to build a model and then to make some cross validation, right? Yeah, that's not good, in my opinion, with this understanding, with this concept, basic concepts. The second important concept that I see is the random correspondence, because that's the point where the mathematics separate with the statistics. So actually I communicated with many mathematicians and statisticians to ask if there's a definition for random correspondence. Nobody gave me. So I did it, actually I did it in 2009. And I defined it in 3 steps. One is point-to-point random correspondence. Then point to subset. And then set to set. I mean with additivity of sets and combination operation, right? For all subsets. So we have these definitions. It means in 100% possibility, or maybe I use the wrong concept. It's a perfect probability over the sample size is guaranteed, since all possible random correspondence are in consideration. There's no certain correspondence in a random space. Do you agree that? Maybe
not really.
you can
Not really.
you can make these definitions better, more professional, mathematical professional.
I just wonder whether you can give concrete examples. For example, when you talk about the first slide, you talk about normal.
Because this basic concept is very important to figure out the methodology.
You haven't go to your example yet?
And then I said this, you will say the one-to-one correspondence. The one-to-one correspondence is a particular case of random correspondence. If the set, if I equal to j equal to 1, I mean each set has only one element, right? So you have a one-to-one correspondence. Several one-to-one correspondence with the same properties and function definitions, they can be combined. So the one-to-one correspondence is a particular case of the random correspondence. So I say this is why we should not take the mathematical certainty orientated thinking mode to solve the problem with uncertainties, as Jean-Paul criticized. Because Hugh doesn't have the concept of random correspondence, so he don't know what is going wrong. But with these definitions, it's easy to understand. For example, in the definition for arithmetical mean, we have a certainty assumption. Mean every sample point has same contribution to the expectation. So each point has a weight equal to 1. That's a certainty assumption. Yeah, so that's why I give this. So once you have this, you are easy to understand, why different sample points have different weights. Because the new method doesn't take a certainty assumption. We take a random. More background. Actually, we already talked about that. Based on the several questions and answers. These are intuitive and common sense in statistics. These questions. Say, unimodal distributions, curve. I draw these figures. So you can say some are skewed, never skewed, some are never skewed. So where is the arithmetic mean? Is it always at the peak? No. No. Yeah. Right. So we have the centralized location. This centralized location for both the symmetric ones and asymmetric ones, all at the peak, without any problem. But the arithmetic mean must be not at the peak for the skewed distributions. So this is the question. The first question is the arithmetic mean? No. The answer is that. This is another picture I drew. So from these figures, you will say this arithmetic means randomly change at two sides of the peak. It is unpredictable. It is totally random. Yeah. So we can say the arithmetic mean is a biased expectation estimate for the skewed distributions. So that's the reason why the t-test or f-test cannot be applied to the skewed distributions, because the expectation estimate is biased, then the variance is biased, then the t value and p values are biased too. Then Is the non-parametric methodology helpful as an alternative of t-test, of the parametric test, parametric methodology? I don't think. Yes, it's helpful, but it does not solve the problem that we are facing in data analysis. The problem is the errors in the data analysis we face with the parametric methodology due to the skewness, right? And the mathematical mean. That's the problem. There's errors in the data analysis. So somebody suggests, okay, we use non-parametric, but the non-parametric downgrades the precision in the result by transforming a real difference among the numerical measures to a rougher difference expressed by sum of ranks. So the result still contains errors. It's not a real one. And the another big problem is when we do statistical measures in data analysis, there's a so-called inconsistency of measurements. For example, for genetic data analysis, we might have thousands or 10,000 genes, right? Some are normal, some are not. So for the normal ones, you might take a t-test. For skewed ones, you might take a rank sum test. But the p-values are not measured in the same method. That's a systematical error that statistics cannot be treated. That's inconsistency in the measurement of p-values. Or, okay, you can take another way. All use t-test or all use the non-parametric. So what's the problem? Errors, right? So either non-parametric or the traditional t-test with arithmetical means doesn't work well for genetic data analysis. So that's the awkward situation we are facing. It's because we lack a few simple concepts and rush to define the centralized location of a population distribution on its arithmetical mean. That's the reason. However, the problem is that we should not always assume that the population is normally distributed. What we can assume is that the population may have a distribution, and the distribution may have a centralized location or center, which may be called population expectation. Actually, in the current system, we don't have this concept. We always, okay, consider the population mean is the population center. We assume that with law of large numbers, but it's wrong. For example, in the genetic data analysis, the distribution might be from the extreme left skewed to the extreme right skewed. Everywhere has, right? So we cannot take that assumption. The population mean is the population center or population expectation. We have sample expectation, right? The concept of sample expectation, but we don't have the concept of population expectation. So I would like to introduce this to the current system. So we'll carefully distinguish the concepts population expectation, population mean, and sample expectation and sample mean. We need carefully to distinguish the difference. So how to estimate a population expectation? That's the major topic today. Before I present the concrete algorithm, I would like to share some ideas. Because these ideas cause that methodology be established. I will take this cursive E to denote the population expectation. It's not known due to the infinity of the population. So we have to take sample to estimate. From this point, the rest discussions will be restricted on sample. We will no longer discuss the population because actually our population cannot be taught, cannot be discussed because it's unknown. But we can assume something with a very simple logic, like this. We just say, hey, yeah, population may have a distribution. The distribution may have a center, right? That's it. That's what we can assume. But we cannot assume it's normal. That's certainly an assumption, right? We cannot. So, suppose we're given a sample like this. This is the one I used donations. Might be different with the current one somebody used in the textbooks. Yeah, in the current statistical we use the arithmetic mean to estimate the E. The question 1 already shown. That is not appropriate. So the logic of algorithm. First, we can show a set of random measures will have a distribution, and the distribution should have a centralized location or center. That's it. That's the assumption we take. The center must be always corresponding to the peak of the distribution curve, rather than anywhere else. Since arithmetic mean randomly diverges from the peaks in skewed distribution curves, as we saw here. So it must be a biased estimate for the peaks. Okay. So we need a new algorithm to estimate the peak. Continuous of the logical algorithm. The arithmetic mean fails because it takes an equal weight. That is an assumption of certainty for each sample point. The formula of mean can be equivalently written this way. I think nobody has questions. Yes. If we describe the relationship between the sample points and its weight in two-dimensional space, it looks like the figure 8. That's the point. This is a line, straight line. Do you think it's appropriate? That's for the arithmetic mean. But in my opinion, it should be in this way. This is another sample I use to show you. It should be in this way. That should be the distribution status of the sample point. Actually, this show you something, yeah, in some sort of right away. It also shows you the density changes in the lines, right? But that's not the best way, I think. This should be the best way that we can do that. Continuous of the logical algorithm. We can sure the peak is determined by all sample points, right? The peak is determined by all sample points without any loss. Okay. Each point may have different relative contributions or weight to the peak due to their randomly variable distance to the peak. Is it reasonable to give this assumption? And then, however, we have no way to know the peak. Where the peak is before we have the weights for each point. We have no way to know the peak. So the calculation of the weights cannot take an advantage of the location of the peak because we don't know the peak. So this means that the peak will be determined by the points, measures, and their weights. So we must obtain the weights before we can estimate the peak. The contribution of a sample point to the known peak is equivalent to its total variation to all sample points, including to itself, since the peak is determined by all sample points. Right? So we don't know the peak, but we know the peak is determined by all sample points. The third is a logical algorithm. This is a structure of a relationship between any two points x1 and x2 in a maximum continuous measurable sample space. The space can be divided to three parts, A, B, C. Right? Usually, we use this, the B, but we ignore the A and C. In many methodology construction, right? So with the arrays 2 and 3, we can say difference. But with the arrays 1 and 4, we can say similarity. Means the 2 points close to each other. Use the array 2 and 3, we can see they are separate from each other. But with the array 1 and 4, we can see they are close to each other. This is a different angle to observe, right? So let's define. Interval B is a relative differentiality between x1 and x2. And interval A plus interval C is a relative similarity between the 2 points. That's the algorithm. So the first step is to calculate the point-to-point relative differentiality and the similarity. I don't use the way of the matrix. I try to use the simple ones. But the operation rules is following the rules of the matrix operation. So you see, we use the absolute value between any 2 points and then divided by the range. So this value is larger or equal to 0 and smaller or equal to 1. If the sample size is n, so each sample point has n differentialities, right? So similarity can be defined in this way. 1 minus is differentiality. That's the first step. The second step is to calculate the cumulative differentiality and the similarity for each point. So it will be larger than 1. It might be very big. For example, if your sample size is very big, that one might be very, very big number. But no problem. According to the definition of this, we have the simple way to calculate the cumulative similarity. It is equal to n minus cumulative differentiality for each point. So you can say the n is divided by 2 parts. Sample size for each point. Yeah. So then calculate the product. Take this multiplied by this, right? Their sum is always equal to n. It doesn't work anyhow, right? So we take a product. This product will be randomly variable. It's not equal to. It's not equal to some to a certain number. It's randomly variable. Nobody knows. But this belongs to the range domain of real numbers larger than 1. Yeah. So it's not good. It's not good for use when it's transfer it to the domain of 0 to 1. It's easy. find the range of the weight and the minimum weight, and then use every measure of the weight to minus this and divide it by range. Then this will be in the range of 1 and 0. However, the R will give you this. It's not what we expected, right? This one should what we expected. So we need to make another transform with this. Why I use the R and the C to denote these two? Because here, what we are calculating is the relative contributions. So first I have the R, and then I have the C. Then once we have the C, then we have this. This is a sample draw with systematic sampling method from a sample. The original sample size is 100. I just take 10 sample points. It is drawn systematically from the sample. I mean, we order samples and then take one in 10, right? Okay. So that's a arithmetical mean. So that's a arithmetical mean, and the self-weighted mean, and then the original sample mean is this. Arithmetic mean, the original sample, the self-weighted mean is this. It's very, very close because that sample is normally distributed. That's the two-dimensional space to show the arithmetical mean and the weight for each point. Yeah. This is to another samples. The two upper ones are drawn with SAS program. The SAS always assume the arithmetic mean is at the peak for either normal or skewed. This is wrong.
Why they don't use median? Why they don't use the median value?
Median is not good. Median is, I will show you. Median is a particular case of this methodology. You will see.
Or mode, M-O-D-E, mode.
No, it's not mode.
Mode.
It's a generalized mode. It's not the mode that we can say in a fraction table. I believe everyone knows the fraction table, right? The mode is the biggest one, biggest frequency.
Mode is by definition, by probability definition, it's just a peak. It's just what
the peak, this peak, you see.
Peak, that's what you're looking for.
It's, I say, you see here. This is the C. We have 2 points. It's at the peak. It's one part. We cannot take these 2 points as the expectation. We should use the self-weighted mean. Not these 2 points as these 2 points. We should not take the real measure numbers as an expectation estimate. Although they have the largest weight, you should know these numbers are random measures. We should use all the weights and all the sample points to figure out that peak. This is not a real peak, actually, because it's a random. This is a random sample.
We have only 5 more minutes.
Oh, okay. Almost finished. Okay. Below ones are calculated with the method that I established. So you say we have 189 points, and this is 2,480 points. This is the skewed distribution. You'll see a tail goes up. This is very interesting. This sample is a normal one. This is a skewed one. You see the arithmetic mean is the green one, and this is the self-weighted mean. So the arithmetic mean will never be at the peak. The properties of the self-weight C, it is measurable for each point in a given sample, and it's a random measure for each point x. It is a random variable, and it is a local relative density measure for each sample. And then for each point, its self-weight contains all information between itself with all the other points in the sample without any loss. And then special case, that's a special case of this methodology. If the sample size is 2, that's arithmetic mean. If the sample size is 3 or 4, it's a median. So the arithmetic mean and the median is just a special case of this methodology. The next question you might ask is the self-weight C the only one way that can bring us to the peak? I believe. Because I didn't lose any information. All information included. I believe, but you might not agree. So let's take a look at the simulation. This one. This is 100,000 points simulated in a normal distribution. In normal distribution, we can see the self-weighted mean almost perfect to the population mean. That's population. Give the population. That's the self-weighted mean. Almost the same. The greatest interesting thing is we have this curve. It's a scatter plot. Directly showing the dispersive tendency and the central tendency of each point. And the terminology that I just say, the self-weight was used by somebody several years ago. I think it's in 2002. But they defined the self-weight equal to the sample point itself. So we have a 45-degree straight line in a two-dimensional space. So this is not good. And also, a Russian statistician, Dodorov, did another attempt almost at the same time that I made the attempt. But he just used the cumulative differentiality. It ignored cumulative similarities. So different people try to find something better.
Did he learn any probability class? Did this guy, I mean this couple, the previous...
You mean the Russian couple?
Yeah. Did they take any courses in probability?
I don't know.
Okay.
I don't know. They published their paper in I think in a medical science journal, psychiatry. I think he used this method to analyze the psychiatry data. Yeah. So unimodal distribution can be described in this way. This is the total variance, this is left variance, and this is the right variance. And this is the self-weighted mean estimate for the population expectation. Then normalization with the self-weighted mean, because we find the peak, just the way we talked at the beginning. The normalization will be doing this way. This is the original one. This is the mirror image one. Both has the same variance. And this is the mathematical relationship between the two distributions, original one and the mirror image one. A double expectation minus the original expectation is the mirror image. So their combination must be a symmetrical or normal distribution. So that's the normalization. You can say we can combine them, and then we have this. What is interesting is that the three distributions have the same expectation, same variance, same maximum measurable space. So the normalization will no longer necessary in data analysis with the peak estimation. Yeah. Thank you.
Okay. So if you have any question, you can ask.
I think what he did is kind of fall into another category of non-parametrics. You know, it's not really, but all non-parametric methods have some theory for behind of them, has some probability, you know, to
but
support
yes,
the
it
large
has
sample
probability
size.
distribution.
I mean,
But you should know.
We have to have a large sample size, you know, probability to support their results. But yours, you just give some method. You're lacking of like you know, probability background to support what you did. Makes sense, right? For example, there are so many distributions. How do you know they have to be a combination of two normals? It could be any normals, right? Like in math, let me give a very similar example. Like in mathematics, every function, no matter how complicated it is, it could be approximated by polynomials, right? You can have poly x to the power n polynomial infinitely close to any function, right? That's a Taylor expansion.
Okay,
that's a Taylor expression.
Let me ask you a question.
Okay, so I haven't finished my point yet. I'm sorry.
Okay.
I mean, so in your case, any distribution, similarly, in my guessing, that's just my guessing, all right? Any distribution can be approximated by the summations of a bunch of normal random variables. A bunch of numbers add up, you know, add up plus or minus, you know. But you cannot just say there are just two of them, you know. Okay, that's my point. Okay, go ahead.
Actually, this new method is for normal distributions.
If you just focus on normal,
because all unimodal distributions can be normalized without any difficulties.
Well, that's the background. You know, the supporting evidence is that behind that statement is centrally serial. Yeah. Right? It's centrally serial.
It cannot be true because if the tail behavior is not like the negative quadratic polynomial term, it cannot be normal even if you symmetrize. So you borrow some weight from the left tail and put it in the right tail. That's the symmetrizing procedure. That may not always give you a normal distribution, but it is guaranteed to give you a symmetric distribution. But that's fine. So thanks the speaker for the presentation, and thanks for visiting here.
Thank you.